two identical helium-filled spherical balloons, each carrying a charge Q. These are the two balloons carrying charge Q and tied to a weight W with the help of the strings. Here it is a weight W, and these two balloons are tied to this weight with the help of these green strings and floats in equilibrium as shown in figure. So most of the information is written on the figure itself. So take the density of the helium as rho He and density of air as rho A and ignore the weight of the unfilled balloon. So which of these options may be correct? So here you can see that three options are based on the charge and one option is based on the volume of balloon. So first of all, let us make a force diagram for this situation. As you can see here in this animation, these are the two balloons. So weight of the body, these are the two tensions acting on the string, opposite pair of the tensions, and the rest of the forces which I am going to explain you right now. So this particular force is suppose F. This is our electric force of repulsion. Let it put it Fe. Fe is the electric force of repulsion between these two charges because of the nature charge. So what should be the value of Fe in this case? So Fe will be what? Q square divided by 4 pi epsilon naught into distance between the charges whole square. So here you can see in the diagram the distance between the charges is 2x. So 2x whole square. So what it becomes? It becomes Q square divided by 16 pi epsilon naught x square. So this is the electric force of repulsion acting between the balloons. And here is the weight of the balloon, and this is the buoyant force. Let it denote with the help of the B. So B is the buoyant force, and here let us suppose W dash be the weight of each balloon, because W is given to be the weight of this block, and let us suppose T is the tension on this particular string. So in case of this particular block, if we draw a line here vertical, we know that this particular angle is theta. So component of T in this direction is going to be T cos theta, and same for this particular tension. And the horizontal components of the T are what? T sin theta. So T sin theta for this block gets cancelled, and the rest to T cos theta, which means 2T cos theta balances the weight of this block. Okay, so this equation refers to the equilibrium of the block only. Now let us analyze for this balloon. So here in case of balloon, you can see that the forces are vertical, horizontal, but only one force, tension, is there, which is needed to be resolved. So let us resolve this force of tension on any of the balloons. So as we know that this angle is theta, so this component is going to be T cos theta, vertical component, and horizontal component of this force is going to be T sin theta. So T sin theta must be equal to the electric force of repulsion between these two charges for horizontal equilibrium at least. In case for horizontal equilibrium, this must be the condition. Okay, so T sin theta is equal to Fe, and here 2T cos theta is equal to W. So this is the equation for the block. So using these two equations, we can write what? Just divide these two equations, we get 2 cos theta divided by sin theta equal to W. W is the weight of the block, and divided by Fe. Fe is Q square divided by 16 pi epsilon naught x square. Okay, so as you can see here that Q can be written as under root of what? Here 2 and here becomes 8. So 8W, and sin theta upon cos theta becomes tan theta. So let it put in terms of tan theta, and one is pi and then epsilon naught and then x square, where 2x is the distance between the charges. So first option will be the correct option to this question. Okay, if you analyze the vertical equilibrium of any of these two balloons, you can get the volume of the balloon. But In this case, this option is not correct. Only one option is correct, so option A will be the right option to this question.